This podcast is brought to you by LMU Munich.
Okay, so what I showed you this morning was a calculation in lowest order of the fermions for basic supergravity. So what we showed was that the following Lagrangian, which is an extension of Einstein-Hilbert by some spinorial coupling to this spin 3/2 field, d nu psi rho, is supersymmetric to lowest order in the fermions with the transformation laws which I gave you. And also we saw that this is in fact true in all space-time dimensions. Because in fact we were only using gamma matrix identities which were totally independent of space-time dimension 4. So then that's a nice property, if you wish, of general relativity in any dimension. There is some kind of spinorial structure underlying general relativity. But now if we want a truly supersymmetric theory, we need invariance of an action, of course, in all order of the fermions. If not, that is not a true symmetry of the Lagrangian. And as you can imagine, and as we were discussing this morning, of course we would expect that the full supergravity Lagrangian is not just given by like a free kinetic term of this spin 3/2 field, but we may have to add other interaction terms in higher order of the fermions, all those terms which we neglected this morning. And so that will be, I'll keep that short and mainly a discussion in words about the quartic fermion terms. Because this structure is still kind of neat and compact, but the structure of the quartic fermion couplings can be quite ugly, depending on the space-time dimension, depending on the matter content, and so on. The structure of these interaction terms can be, of course, much more complicated than this simple kinetic coupling we had here. So in fact, nowadays, when one works with supergravity, on the classical level, these quartic fermion terms, you will hardly even see them mentioned in the papers. But when supergravity was constructed in the 70s and the 80s, of course, the main thing was that there is a consistent extension of this action such that it is supersymmetric to all orders. And as I will discuss, that only holds in very few space-time dimensions and with very particular extra meta content of these theories. So in fact, there's only like a handful of well-defined supergravities which are supersymmetric to all order in the fermions. Whereas what I've written here is really true in all space-time dimensions. So let's say in general, supersymmetry fails at psi 4. At fourth order in the fermions, typically this Lagrangian is no longer supersymmetric, and you cannot even make it supersymmetric by any possible interaction terms you could add to it. And remember, if we add higher order fermion terms, it's not just the Lagrangian, it's also the transformation rules which we will change. So that can be a chain of adding here, adding there, modifying here, modifying there, so that can be really complicated. And that's why it took quite a while before people completed these theories. In general, it fails, and it's only true, first of all, in very particular space-time dimensions. You probably have heard, in fact, an upper limit on the possible dimension of space-time is 11. So beyond 11 dimensions, there's no possible completion of this Lagrangian into a supersymmetric theory. And not only particular space-time dimensions, but also in general, we will be obliged to add additional matter to the Lagrangian to make it close into a supersymmetric theory. So in particular space-time dimensions with particular additional matter like vector fields, p-forms, and so on. Now, in order to calculate quartic fermions, I will not go into the details, but that is computations which are more lengthy than what we have seen this morning. So I'll not go into that. Let's just say calculations are more complex. In particular, we need two kind of extra techniques. One is the so-called Fiat's identities. Which tell you that if you have a product of spinors, say of 3 and more spinors, usually there are non-trivial and non-manifest identities how you can reshuffle the order of these spinor fields. Cubic or quartic in the fermions. And also it turns out to be very useful to go to the first order formulation of these theories. In which you consider the spin connection as an independent field. And then by its field equations, it takes the form of the spin connection we have been putting into the theory. First order in the sense that the standard Einstein-Hilbert action, first order in derivatives. The standard Einstein-Hilbert action is a second order derivative action in the metric or in the field line. So basically it has like d, e, dE terms and so on. Right? But if you look closer, actually the form we have even written it in terms of the spin connection. I could interpret it as a dE times the omega term. Now if I treat E and omega as independent fields, then this would be a first order Lagrangian in the fields E and omega. Okay, so first order formulation means rather than a second order function of the tetrad, I consider a first order function of the tetrad and the spin connection. And now I have an additional field equation because I can also vary with respect to the spin connection, and that will give me an algebraic equation which expresses the spin connection as a function of the field line.
So it's W dependent.
Say again? This Lagrangian?
Yeah.
In this Lagrangian, well, yes, this Lagrangian is W dependent. Remember the Lagrangian we had been writing out was also W dependent in the sense that we had some proportion, whatever. We had some appearance of the spin connection here. Okay, but we consider the spin connection as a function of the tetrad itself. Okay, so in some sense this is really just a single function of the tetrad. The spin connection is purely formal. It's a function, it's a fixed function of E. And then it's a second order action in E. Okay, but I could as well, okay, I'm giving more. I could as well write down an action like this. I write exactly the same. Simply, I don't say that omega is that omega which I gave you. And I say omega is a free field. And this is just the connection of, free field. It's a fundamental field in itself. And this is just the curvature of that free field, of that fundamental field. And now I have a Lagrangian which depends on two objects, namely the tetrad and the spin connection. And so I will have two equations of motion. I will have roughly dl dE is 0, but also dl d omega is 0. So I have twice as many field equations as I had before. And these field equations basically will give me the expression for omega in terms of the spin, the tetrad and so on. Okay. So it's like second order formulation. And that would be a first order formulation. First order formulation in terms of twice as many variables. And it turns out to verify supersymmetry. In fact, this form or this formalism turns out to be much more useful to really verify supersymmetry if you want to see all orders in the fermions. Because here terms really shuffle by themselves, they organize nicely and in a compact way, whereas here you have to really to work very hard to keep track of all the fermions. Okay. In fact, what is even more useful, but I will not say about something like this, is kind of a mixture of these, which people call the 1.5 order formalism. But I don't think I will say much about it. If you want to see how that is done, how to treat quadratic fermions, it's nicely given in those reviews which I put on the sheet, for example, the one by Tani or the one by van Nieuwenhuizen. Okay, they give you a very detailed discussion how the quadratic fermions work out. So that's the result. Let me just give you the result. Because now that is really specific to the space-time dimensions. So in 4 dimensions, this supergravity Lagrangian can be really made into, say, L sugra is supersymmetric in all orders of the fermions. So that's the famous result about 4-dimensional supergravity, which was done in the 70s by Friedman, Ferrara, and van Nieuwenhuizen, and then later by Deza and Zumino in the first order formulation. So when they did it first, they really did it in the second order formulation, where you have to try really hard to compute quintic fermion terms and all that. But the way which organizes the computation neatly is the first order, or this 1.5 order formulation. Okay, so I think that's all I want to say about that. Again, usually nowadays people don't talk so much about quadratic fermions, because at the classical level, most of the information about the theory we see already in the quadratic fermion couplings and then in the bosonic sector. Okay? But in order to be sure that the theory really exists, of course it's a big thing to know that there is a fully supersymmetric theory behind. Okay, so quadratic fermions are essential in the beginning, but then sort of you can kick the ladder and just look at the quadratic terms and the bosonic sector. Was it? No? Questions to that? Okay. So it works in 4 dimensions, but in all other space-time dimensions, it requires a new investigation. Can you make this supersymmetric or not? For example, in 5 dimensions, Turns out you cannot make this supersymmetric unless you add an additional vector field to the theory. So in 5 dimensions, you need one more vector field, and then, of course, also vector gravitino interactions. And only then the whole thing will turn into something supersymmetric at the higher order in the fermions. Let me maybe want to mention some small extension of this theory to ADS supergravity. Here we are already talking about some extension of supergravity. So here we just were supersymmetrizing Einstein's general relativity. The simplest extension of general relativity you can think of is adding a cosmological constant to the Lagrangian. You can ask, can we still make this supersymmetric if there is a cosmological constant in the Lagrangian? And since I'm a bit over time in my schedule, maybe I give you, I pose this as an exercise, which is in fact a neat little calculation which you can do if you want to get some feeling for these gamma matrices, which is a bit at the level of those quadratic checks we did this morning. So here's the statement. The anti-de Sitter Lagrangian, take the supergravity Lagrangian which we had this morning. Let me be more specific. Take Einstein, Hilbert, and Rarita-Schwinger. Add a cosmological constant term, say with the constant alpha 1, square root of the determinant. That's it. Now, of course, if we modify the Einstein-Hilbert term by cosmological constant, we presumably also have to modify the Rarita-Schwinger term to get some compensation of this term. And that is indeed true. And there's a term which looks like a mass term for the gravitino. It goes like this: psi bar mu, gamma mu nu, psi mu. With another constant, the constant is here, another constant alpha 2. Okay, so that's like the simplest extension of that supergravity Lagrangian, a cosmological constant and a mass term for the gravitino. Now, can this still be supersymmetric? So can these two cancel under their supersymmetry variation, and these two in the same way? Turns out the answer is yes, if you also allow to slightly modify the supersymmetry rules. For the Vielbein, I keep the previous transformation, but I slightly modify, and that is something, in fact, which is rather typical structure in supergravity, which we will see showing up again and again. I slightly modify this variation, which used to be just the derivative of epsilon, of the parameter. I modify it by something which looks also like a, well, put a coupling constant g, gamma mu times epsilon. Okay, it's like a mass term which you add into this derivative. G is a constant. G is a real constant. Okay. And the statement is, if you do that, so you slightly modify your transformation rules, you slightly modify your Lagrangian, all this can be made consistent if these constants are chosen as the correct functions of this coupling constant G. Okay. To check that is a nice little exercise in gamma matrices, so if you want to check that exercise. This is supersymmetric. For proper choice of alpha 1 and alpha 2. And again, this holds in all space-time dimensions. And again, at the lowest order in the fermions. And to see if it really extends to all order fermions, you will have to check separately. In general, it will fail at lowest order. And one thing you will find here is that it works, but the value you will find for this constant alpha 1 will be positive. Roughly, alpha 1 will be something like g squared. And since g is real, there's a definite sign of the cosmological constant. Now, alpha is positive means that the potential, think of this as minus potential, is negative. So positive alpha, in fact, corresponds to negative cosmological constant. And that's why we call it, well, it's not de Sitter supergravity, it's anti-de Sitter supergravity. Okay. So supergravity can also work in presence of a cosmological constant, but only if that cosmological constant is negative. Okay. And that is in accordance with the fact that we know there are supersymmetric extensions of the ADS algebra, but there are no supersymmetric extensions of the de Sitter algebra. And again, this, okay, let me make more and more remark. In all orders, because that's the crucial test, is it true to all orders in the fermions? It's true in all orders of fermions for four space-time dimensions. I think that goes back to Townsend, who proved that the first time. But for all other dimensions, we will have to check case by case. For example, 11 dimensions, which is the highest dimension in which we can construct a supergravity. In 11 dimensions, there's no consistent extension by cosmological constants, okay, in supergravity. Even though it works at the two fermion level, it will fail at the higher orders in the fermions. Okay? But for certain cases, it can be made true, and it's this kind of structure which shows up. Any questions about that part?
So you have patterns that arises to show that it's true at all orders.
Say again, it's true in all orders?
Do you have patterns that appears that arise to show that it is true at all orders? And obviously they did not calculate that at the orders.
You mean for the anti-de Sitter or for the start? Basically, the computation for the anti-de Sitter is just an extension of the structure for pure supergravity. So the fact that four-dimensional supergravity you can extend in that way by cosmological constant, and the fact that it works to all orders in the fermions is more or less a consequence of the fact that it worked here and the way the quartic fermions show up here. Okay, but to give more details would become much more technical. It's the fact that these quartic fermion terms, they are not totally random, but they have some certain pattern behind them. Okay. Roughly, they have the pattern. They look like the standard supergravity, only the terms quadratic in the fermions, with a modified spin connection. Okay. The structure of the quartic fermion terms can all be absorbed into simply a modification of the spin connection by a torsion term. And that torsion is bilinear in the fermions. So there is a hidden, very compact way to phrase all these quartic fermions, which is true in 4 dimensions, not in general, but in 4 dimensions that is like that. Okay. And so there is some very compact way of writing this theory. And once you have understood this organizing principle behind, that also allows you to add the cosmological constant. But in other space-time dimensions, it may be more complicated, and that's why in other space-time dimensions also, it doesn't necessarily hold that I can simply extend things with a cosmological constant. Other questions? Okay, so that was all I want to say about what I call basic supergravity, the simplest possible supergravity theory, just Einstein-Hilbert plus Gravitino. But of course, what you will meet in practice is not this theory, but is more complicated and extended versions thereof. And all that I will group into this name of extended supergravity. So the very first extension of, yes?
When you are talking about all dimensions, this holds also for 3-dimensional linear supergravity?
Yes, that's right, yes. Again, to the lowest order in the fermions. Whereas in 3 dimensions, I believe it goes through to all orders in the fermions. Also, you can make it totally supersymmetric. Yeah. But this is really, to lowest order in the fermions, this is true in space-time dimension 32. Even though there is no supergravity in 32. Okay? It will fail at the higher order fermion terms. But in 3 dimensions, 3 is typically very well behaved. In 3, you can make this into a fully supersymmetric theory. You add some quartic fermions, and that will be a fully supersymmetric theory. Okay. So what we had there was really the first simplest extension of supergravity by just one parameter, a cosmological constant. Okay. So you see there's one free parameter in that action, this g, the coupling constant. All the coefficients will become functions of that coupling constant. Now, of course, in general, we could hope to do much more complicated things, not just add a cosmological constant, but maybe add other matter fields to this Lagrangian. Okay? Do quantum field theory with scalar and fermion fields, but coupled to not only to gravity, but to supergravity. Now, in order that it works nicely with the supersymmetry, I should not add arbitrary matter, I should add matter in supermultiplets, in n=1 supermultiplets. And those are easily classified, so those are representations of the super Poincare algebra in 4 dimensions. You may have seen them. They have a very simple form. So, in terms of the helicity of a 4-dimensional field, which can range from -2 to +2. The multiplet which we have been studying for the moment was a multiplet which has just the metric and its superpartner. So it has a state of helicity +2 and a state of helicity +3/2. This is g mu nu, this is psi mu. And indeed this is like the simplest, it's one of the simplest massless multiplets of the n=1 super Poincare algebra. And then since we're writing on the field theory, we also need to add, because the completion, so the minus helicity states -2, -3/2. So that was supergravity, which we have been discussing for the moment. But there are other multiplets, other representations of this superalgebra, they look pretty much the same. They're just translated in helicity. Okay? So basically, there's the next multiplet which would carry these two states. The next multiplet carries these two states, and the next one carries these two states. Okay? So we're talking about n equals 1. That means we have like one supercharge. It basically means you have one bosonic state, and with the action of the supercharge, you come to the fermionic state. And that's it. When I act twice, it's 0. Okay, so the structure of the supermultiplet is pretty simple. It's just n equals 1. That is what happens here. But again, we need to add the CPT completion. Tack. Then here we will have minus 1/2 minus 1. And here we will have minus 1/2. But this will bring in another scalar. So in fact, this has two scalars, not just one. 1 because it's 1, 1 plus 1, 1. Okay. So these are the possible multiplets. This is the, you could call this the Gravitino multiplet. This is the vector multiplet. So it carries, what does it carry? Helicity plus 1, helicity minus 1. That's a vector. And then a fermion, helicity plus and minus 1/2. And this is a multiplet which carries a spinor and then two scalar fields. That is a chiral multiplet. Okay? And maybe you have seen supersymmetric theories which you can construct with these theories. You can discuss that even without any supergravity. For example, there are many supersymmetric theories just in terms of the chiral multiplet. Okay? Forget about supergravity, coupling to vectors and all that. The Wess-Zumino model is just a supersymmetric model. It has global supersymmetry and it's given in terms of chiral multiplets. Or you have super Maxwell theory, super Young-Mills theory would just be a combination of these super vector multiplets. So it has vectors coupled to spin 1/2 and so on. But now we are interested in supergravity, so we want to couple matter in these multiplets to supergravity. So let's just make a few remarks about that. The chiral multiplet, for example, its bosonic matter is scalar fields. So let's look at what are the couplings of scalar fields in supergravity. So how do you couple a scalar field to gravity? Well, that we know. We just write a standard, say, Klein-Gordon type theory, but on a dynamical metric. So here we would have, say, scalar couplings. And the most general scalar couplings we can think of, well, there's the space-time metric g mu nu, which contracts a d mu phi, d nu phi. Okay. Imagine we have a bunch of scalar fields, we have a bunch of these chiral multiplets, they carry some index I, and so this will be the most general kinetic term. But since scalars carry some index, because we have several of them, we need some matrix which contracts them out. And since we don't assume anything for the moment, that matrix itself can depend on the scalar fields. So there could be some g ij, which in itself depends on the scalar fields. So that's the most general kinetic term. If you stick with a second order Lagrangian, that's the most general kinetic term you can think of, which couples scalar fields. And then what else can there be? Well, it's scalars, they could also have a scalar potential. Right? So there could be some function depending on the scalar fields which takes the role of a scalar potential. And roughly for the scalar fields, that's it. Okay? So the scalar couplings basically encoded in two objects in this matrix Gij and this function V. And this matrix, as you see, it is symmetric. It should be positive definite to make this a well-defined ghost-free Lagrangian. So this is like a metric on a space whose coordinates are the scalar fields. So that's a metric on the target space. So we can speak about curvature, connections, and all that things on this space of scalar fields. And then there's a scalar function living on that same space, and that's the potential. Okay. So basically, the structure of that of those couplings are encoded in some geometry, the geometry of the scalar space, and some function on that scalar space. Now, of course, if you choose here an arbitrary manifold, an arbitrary function, then in general this will not be a supersymmetrizable Lagrangian. So the fact that we can couple this to supergravity and that we can make all this into a supersymmetric theory will pose some constraints on these objects. So supersymmetry poses constraints on Gij, that is to say, on the geometry of the target space, and on the choice of that function, which is the scalar potential. But if you make the right choice, so there will be a number of constraints which these guys have to satisfy. But the moment they satisfy these constraints, all this can be made into a supersymmetric theory. And there will be fermionic couplings which carry these spin 1/2 fermions, and they will couple to the gravitinos, and there will be quartic terms, and everything will be very complicated. And you can find the precise form of such theories, for example, in the book by Friedman and van Prooijen, which I put on the list. You find the explicit form, all the couplings of the Lagrangian. But for sort of keeping track of what's going on, the easiest is just, let's concentrate on these two scalar functions. They contain all the information. Almost. Okay? Basically, everything is in here, in the choice of the metric and the choice of the potential. All the other couplings then are determined as functions of these objects. And now for n equals 1 supersymmetry, the structure is in fact very simple. For n is 1, so a supersymmetric extension of what we have been constructing this morning. N is 1 imposes that Gij is the metric of a Kähler manifold. Okay, complex manifold. You see, we always, since scalars come in pairs, there's always an even number of scalars. They should be the coordinates of a complex Kähler manifold. So what does it mean? Without going into many details. So there are some coordinates. There are complex coordinates on this manifold. Since we have an even number of scalars, we can group them in complex coordinates. So say phi I and its complex conjugate, phi I bar. With a metric whose diagonal blocks are 0, so Gij is 0, and so is Gi bar J bar. And the off-diagonal block, Gi J bar, is of a very particular type. It's the double derivative of a real function, the so-called Kähler potential. a real scalar potential. Okay, so that's a pretty constrained structure. So in fact, rather than dealing with a whole metric, we are just dealing with another scalar function, which is the scalar potential. So the data for describing scalar couplings in n equals 1 supergravity is just this real function, the scalar the scalar potential, and then possibly a scalar potential V. Okay. And all the remaining couplings, the fermionic couplings, which I repeat become very complicated, very lengthy, so I'm not going to spell them out, but everything is encoded as functions of this object. Okay. The structure of the potential I will not discuss in detail. That's a bit more complicated. Again, you find that in great detail in the book. Well, let's just say the structure is more complicated. We will see examples later, some sub-cases. Various contributions, called the D term, the F term contributions. Some constraints which this thing has to satisfy and so on. But as for the geometry, as for the kinetic term, all there is this structure of a complex manifold. So that's what scalars do in supergravity. Now we can go for the next one. There is the vector multiplet. It carries just vectors and a spinor. So how do such fields couple? Again, we can guess most of it just by looking at the structure of a four-dimensional Lagrangian, which has Lorentz symmetry, gauge symmetry, and so on. See, the vector field has only helicity states plus and minus 1. There's no helicity state 0. This is a massless vector field. All we're talking about here is massless multiplets, in fact.